Okay. If not, then we move to the next session, which is the plenary talk given by Dr. Jan Blommaart. Since we are concentrating today on quantum chemistry, so we will get a talk about quantum computing roadmap for chemistry and the quantum simulation. Perhaps Dr. Taha would like to make some introductory remarks about Jan, and then we go on.
Yeah, thanks, Dr. Ahmed. Of course, Jan and I close collaborators indeed in several projects. Jan is pioneer in terms of quantum AI and also the consulting and the use of data analysis and data science. He's a managing partner of Biodec. And recently, together as the university now, Amsterdam University of Applied Sciences and Jan Blommaart, we have got, and also with our partner ESTRON, the Dutch Space Institute, we got a grant to use quantum computing for spectral analysis for future telescopes that will be launched in a few years. And we do some work now on HHL algorithms, and hopefully to use this for quantum machine learning and advance more of Hamiltonian design. So Jan, perhaps if you like to highlight more, you also feel free to. So.
Yes, good evening. Thanks a lot, Dr. Ahmed and Dr. Taha and other presenters and the students that are participating. First of all, I would say greetings from Amsterdam in the Netherlands. It's pretty hot and it's nice weather today. Almost like in Egypt, Alexandria or Cairo. But there's
You're feeling hot in the Netherlands right now?
Yes. Well, hot. It's still in the evening today. It's still about 20 degrees, which is pretty hot for the month of end of April. Yeah, that's exceptional. But obviously, we also notice the effects of global warming, and I guess it's part of it. Let me share my slides 1 second. I need to find them here. Where is it? Wait. Here it is. Can you see it now?
Yes, we do.
All right.
Quantum-centric supercomputing. Very interesting.
Yeah. So this will be a talk more about how the future is developing in the coming years. As we know, let's say the status of quantum computing as this since, let's say, end of last year and in the first half of this year, we do know it is starting to work in reality. Yeah. And people can study, can do little experiments, and slowly we are going to see that you can do larger experiments. And so the systems are getting bigger, scaling up. Yeah. And now more and more we see that we need to integrate between the classical systems that we have always used and the quantum computing that we are starting to use. And the integration will be done, and it needs to cover more than just quantum computing elements. Yeah, it needs to cover graphical processing units. It needs to cover what I would call classical CPUs, and later on perhaps even memory-centric computing, neuromorphic computing. We'll see how that goes. At the same time, technology is still evolving. Yeah, and new kind of technology, qubit platforms will come, and we need to be able to integrate those. Yeah, so we need what I would call an open design. Yeah, so that you can integrate future technologies and all kinds of software. Yeah. As you have learned already, and you probably go on learning about it and doing your own experiments. The quantum computing as we know it is very good for Hamiltonian simulation. Yeah. It will become better for optimization. Yeah. Not yet, but it has good potential probably. More and more we are learning about quantum machine learning, and another area that is probably pretty good for quantum computing is partial differential equations. So these 4 cases are, yeah, I would say for the coming couple of years, they are the way to go. Yeah. Now, we need integration, we need a roadmap, we need a kind of architecture that will evolve in the coming years. Yeah. And it will start with something where we are, let's say, this year and the coming few years, what we call phase 1, where we have specialized quantum compute engines. Yeah. A bit like when the first graphical processing units were introduced a couple of years ago. Yeah. A kind of offload engine. Yeah. And then we will go to more integration. Yeah. And then in the final phase, we will have truly integrated systems where we have advanced integration software, unified programming models, and all the system software that goes with it. And here you see how we think that the coming years will be developing. Yeah. So we are now in the beginning of phase 1. Yeah. So that will be for this year and next year up till 28. And then in 28, 29, we will start to see the first more integration. Yeah. And then later in the next decade, we will truly see tightly integrated systems. What I could say is that this is the same what you saw with high performance computing 10 or 20 years ago. Initially, we had single processors and a kind of co-processors. Yeah. And then we started to have more parallel systems. And in that design, you could see that the overall performance, the throughput of the overall system, was determined by the slowest part. Yeah. And that's what you want to avoid, obviously. Yeah. And the same is going to happen in the coming years. Yeah? Today, as we speak, in April, May 2026, the quantum computing part is still relatively slow compared to the high-performance classical computing part. But that will change in the coming years. Yeah? And then you really need integration. Otherwise, the slowest part, and that may be the classical part, yeah, in a couple of years, will determine the overall throughput. Yeah. So, and you can only address it if you have a real tight integration. Yeah. that has to do with memory, with bandwidth of all kinds of interconnects. There's no other way. You must integrate it in the end. Yeah. Otherwise, you can never achieve the advantage of quantum computing. And here you see the different layers, yeah, the software layers that we need to address. Yeah. Obviously, in the top you will find the application. Yeah. And most of the people, like us, students, yeah, and application programmers, will be in the application layer or in the application middleware layer. Yeah. But if you go deeper and in the lower layers, obviously, there you will find the real integration, systems programming, security, all those things. Yeah. They need to be addressed. Otherwise, the top layers will not function. Yeah. And you can learn a lot if you look at all these individual components. Yeah. And they also show that you need open interfaces so that you can introduce another component or replace a particular component with another one. Yeah. And that's the way to go. It will never be a closed system in that sense. You will find Qiskit, obviously, but you will also find other programming toolkits. Yeah? Here you have the ticket and circ example. And you will find the parallelization libraries, yeah, in the classical part, I would say. And here is a flow once we have, let's say, more advanced error correction in the coming 2-3 years. Yeah. And there you can see how the software is executed. Yeah. And at the level of internal, in the middle, yeah, that will be totally abstract. You don't notice it. You will program in higher level languages, and it will be transferred to the kernel. So now, as user, as students, as developers, you will use Qiskit or another programming toolkit. But in order to achieve the tight integration and the reliability and the overall performance of these systems, there are other aspects that need to be addressed. Yeah? You need fully cloud integration, obviously. You need all kinds of systems management, monitoring. You need every aspect of a security architecture. And you need this open integration in order to be able to introduce new technologies, new qubit platforms when they come available. Yeah. So, yeah, this is, I think this is the way to go. Yeah. And we need everybody, all kinds of vendors, developers, and systems integrators to work together to make this happen. This is the story. So, conclusion. Quantum computing will become integrated with classical systems. And those new integrated systems will become quantum-centric supercomputing systems. They will complement the current classical high-performance computing systems and partly replace those. And this is going to happen in the coming years, and we will see the first real examples around 29, I think. Maybe a bit earlier, not later, I guess. Thank you for giving you this talk, and I'm ready to take your questions.
Well, thank you very much, Jan. Very interesting talk.
Shall I stop sharing, or shall I keep it in the...
Perhaps keep it for a few minutes in case somebody has a question that might require you to refer to a slide or something.
Okay.
But very interesting indeed. Are there any questions from the audience, or shall I start myself? I have about a couple of hundred questions.
Go ahead.
Roger, Sally, happy to see our CM in stack. Okay. You have a Excel budget for what? I think this is related to something I'm not following. Well, until we have.
Yeah, I see the question as well. Yeah.
Okay, until somebody asks a question, I wanted to raise a point.
Yeah.
Quantum computing research and the industry are always hoping, or in another way, waiting for the day until we get a perfect quantum bit. What if we never get it? Do you expect that we should be developing some computing model with imperfect quantum bits, something similar to what other people did in classical computing when Lotfizada started the paradigm of soft computing, where you combine fuzzy with probabilistic with evolutionary. So these are the paradigms of computing that deal with uncertainty, since we realize that we cannot get rid of the uncertainty. We have to compute with uncertain systems.
Yeah.
Do you expect that we might go this direction at a certain point with quantum computing?
I'm gonna say something. Maybe it's not an answer to your question, but yeah, just let me know what you think about it. I believe we will not develop the perfect qubit. Yeah. And there is a good reason for it. If you have an imperfect qubit, then and we apply error correction, yeah, then that will work at some stage. Yeah. However, if you make the physical qubit every time better and better, it will be more difficult to apply error correction. It will be more difficult to apply particular programming models. It will be more difficult to apply mid-circuit measurement and mid-circuit resets. Yeah. So, in fact, the conclusion would be that we should not develop the perfect qubit. Yeah. Although I know it's very attractive to make every time a better qubit. Yeah. But that probably should not be our goal. Yeah.
Yeah, actually, it looks like for classical computing, it was the same. People kept looking for like perfect computation, and then we ended up learning to deal with the uncertainty.
Yeah.
Because sometimes the uncertainty is an intrinsic part of an intrinsic component of the system. You cannot get rid of it. You cannot. It's not even good to get rid of it. It is part of the system, so it has to be part of the computation. Capture it and do the computation with it.
Yeah, yeah, and what I think is the following. It's extremely important that we look at several aspects at the same time. Yeah.
Mm-hmm.
One aspect is real cost per unit of compute production. Yeah. And I think most people, including myself, I think, underestimate how important that is. Yeah. We you know, we get a bit spoiled because we can compute almost for free. We can do experiments almost for free. But in the couple of years, let's say from 2030, when companies and governments and laboratories are going to really execute real problems with real programs and real quantum circuits, then cost will be extremely important. Yeah. And so that's one aspect. The other aspect related to it is the real speed of execution. Yeah. Not the speed of execution of one little part, but the overall performance, the overall real performance of the overall system. Yeah. There is somebody who should go on mute, I think.
Yeah, somebody, Dr.
Yeah, I
Farh, could you
couldn't define. Yeah, I couldn't find because I see now two mics, so I couldn't find who's really causing this. That's a problem.
Okay. Anyway, and obviously the quality and the quality and the relaxation times of a particular qubit, they are very important. But I would say in combination with cost of execution, the real speed with as you measure it externally, all of that, and then obviously scaling up, because I mean we can be happy obviously with the systems that are available today, but they are still far too small. They need to be much bigger in the coming years in order to really do real work. And what I said in the beginning, integration will become very important, and that's not easy, because you have to incorporate so many aspects. It's optics, it's cooling, it's power supply, signaling transfers, bandwidth.
and the programming model itself.
Yeah, I mean,
that's the big
no, it's let me see where I am with my 1 second. Here. yeah, the software, yeah, for the user, the application developer or whatever, the tester and the business developer or the researcher. Yeah, they are most of the time in the blue and in the green layer, yeah, and everything that is on the lower layers beneath that should enable the green layer and the blue layer, yeah, and that is that will be very complex in the coming years, but extremely important, yeah, to make it happen. And then you have here the gray areas as security, systems management, and the cloud software. So a lot needs to be done still.
Yeah.
Okay.
Okay, we have another question. Are FPGAs and GPUs intended to run classical workloads only or to run quantum simulators too? And the question is related to the HPC and the quantum hybrid model.
Yeah. What is maybe I'm gonna say something that is obvious to you already, but I will still say it. I have the impression that often people stay testing quantum software in a simulator on a classical computer, yeah.
Mm-hmm.
While we should be running on real quantum computers, yeah, because that's the way to go, yeah. So the GPU will only help in the classical simulation, yeah. But the aim should be to run real quantum circuits on real quantum hardware, yeah. And then obviously we have the integration, which is partly quantum, partly classical, and there in the classical part, obviously the GPUs can still have their role, yeah. But the relative position will definitely change, yeah? Once the quantum part really gets speeding up, yeah. That can never be achieved in GPUs. The only thing, the only thing, an important aspect is the data, the bandwidth access to memory, yeah. That's still the relative weak point of a quantum computer, yeah. But there are ideas to improve that, huh? So we'll see how this develops. There are some very new ideas on to have another mapping of data on memory, and then maybe it's less of a problem than we think today, yeah.
Okay.
But that's interesting, very interesting indeed, because
yeah.
Many new ideas still need to be invented and tried out and explored, yeah. A lot that needs to be done still. So there's a lot of work for everybody, I would say.
Yeah,
and I can.
Yeah, go ahead, please. Go ahead.
I mean, it's yeah, what you you need to think about the kind of problem that you want to address, yeah. So investigate the nature of the problem, and you need to combine that with knowledge quantum computing and developing quantum programs. Yeah. So that's going to be a relative difficult part to be able to understand a business problem or a research problem and mapping it on what a quantum computer could do. Yeah. Yeah, we need many different disciplines. Yeah.
Yeah.
Yeah. And
we have two suggested ideas in here. One of them from Mina. Since we model uncertain systems, an imperfect qubit is what is needed. Well, that's a very difficult and complex statement to elaborate on. Maybe, what do you think about that, Jan?
Yeah, let me 1 second. Yeah, that's there are different words mixed, yeah, with similar or different meanings, because once we have real fault-tolerant quantum computing, yeah, the most of the errors in the physical quantum systems will go unnoticed. Yeah. Still, to think about uncertainty, yeah, and what it means is very important. Yeah? But it's not the same as an error in a physical qubit. Yeah.
Yes. Yes.
So that's I hope I made myself clear. So it's a very good point to introduce uncertainty, yeah, in a model, in optimization, all kinds of things, in weather forecast, in whatever you have, and the concept of uncertainty is difficult, yeah.
Yes. Yeah.
But it's not the same as
it's
not the same as an error in a qubit, because later on, with error correction, the errors in the qubits will go unnoticed. Yeah.
Yeah. I also advise Mina to read about uncertainty in soft computing systems, even in classical computing. There are different types of uncertainty. There is the fuzziness in fuzzy systems, which is different from the uncertainty of the probabilistic systems. Again, it's difficult. It's different from the uncertainty of the evolutionary system, where you don't know exactly how the system is going to evolve. So these are different types of uncertainty. And we add to them another fifth type of uncertainty when it comes to quantum systems. So the mapping between imperfect I think we will end up having to do we need to develop computing paradigms to develop with imperfect qubits. But this doesn't mean that we will be computing with the errors in qubits. So the type of uncertainty is different in here indeed. Another idea from Roger Sully. We can use GPU for the second quantization, that is, for example, Fourier transform. I think this is elaboration on the idea of using the GPUs and FPGAs between classical and computing systems.
Yeah. Yeah, the thing is, maybe GPUs will become less important in relative meaning, because the future CPUs will have many GPU functionality fully integrated in it. Yeah, but that's a bit how I see it. Yeah, but okay. I don't know. Is my time over, Taha? What time is the next talk?
Well, it's about time to conclude now, but the talk is really very interesting. So if you have a couple of ideas to elaborate on, and I agree with you that the need for GPUs are going to diminish kind of
well, it's
for many reasons.
What I see is that in silicon development, in chip development,
yeah,
the relative cost of one simple transistor or one simple gate or whatever you call it is going to go down and down and down. So in a couple of years, you probably don't use, I think. Yeah.
Yeah, another reason for that, by the way, is that reports are coming that the need for training models, which is the highest need for GPUs nowadays, is going to decrease because you will reach a point very soon, by the way, in a year or two, where you have trained all the models that you need. So the need will be more for LPUs and CPUs rather than
yeah, that may be true. Yeah, it's.
So I can actually add a little perspective here. I worked for AMD for 13 years until last year. So I was part of the architectural modeling team for the MI400 Instinct. Had worked on probably 5 generations of graphics architecture up to that point. So you're absolutely right. The actual ultimate is to co-locate CPU and GPU on the same silicon. And that's why AMD originally bought ATI, so they could do that, because it was very important to have a GPU when you had like a single core CPU. And then we had lots more cores. And the idea of actually having that co-location, which is called an APU, is actually, I think, something that has a big future. And the reason is that it totally removes the bottleneck of the PCIe. If you have shared memory between the CPU and the GPU, you can get extraordinary performance. So the more you can do on chip in shared memory, and there's a whole architecture for this called HSA, Heterogeneous Systems Architecture, which was developed in, over 10 years ago, and is actually ROCm is rebranded this open source architecture. So all that you can do in open source now is program the CPU and the GPU together. But the reason I brought up the Fourier transforms is I come at the quantum from the idea that, from Dirac's idea that quantum field theory, that in fact, the photon is a quantized Fourier field coefficient. So what we need to do is take our classical data and transform it into the second quantization, make it a field, and have interference in the field. So we can do that very easily because you multiply the fields together and then you do an inverse transform and you get a result. So my it's not the tensor model. It's very much a Dirac model. The ultimate Heisenberg uncertainty is between the particle and the wave. And the only reason this exists because the field is actually, the source of reality. It is the fundamental source of reality. There is no, when you get down to quantized energy, there is no identity, there is no locality. It's a quantized coefficient in the field. Now, how that field is described is problematic for physicists because they can't actually say if it's local or, you know, or not. But I think for quantum computing purposes, we can take an ideal Dirac point of view and say, actually, time is a way of flowing between the dual domains of where you're, consider a, you know, where a photon starts. It's a discrete energy in a, you know, space and time. Then it travels as a wave, and it travels through all paths, interfering with itself. And while it does this, no time has passed. But it finds out through all those paths the optimal position and time to come back and as a photon land on a leaf and you know, promote an electron energy level to be raised, and so we're here. You know, this is my view, so that's why I brought up the second quantization, because I think it's fundamental.
Yeah, it's very intriguing idea.
Yeah.
So, and then we have yeah, Roger. So thanks for that. I mean that for sure. The coming generation of quantum computers will also enable very fundamental physics research. Yeah, it's not only business problems or large optimization problems, but also, yeah, very low level fundamental physics research. Then okay, then I see maybe we take that as a kind of last question, Dr. Ahmed. Can we know more about QRAM?
Yeah, but actually, I think this question is out of scope for this event. I don't know if you want to elaborate quickly about that.
Yeah, I can say something very quickly. From what I know, yeah, and I know little. It's for the coming years, the coming couple of years, QRAM will be introduced as part of a quantum error correction architecture. Yeah, I don't know what will happen after that. Yeah, maybe later on we will have QRAM as a useful QRAM memory, but I don't know. Yeah, for the coming years, it's an essential part of particular quantum error correction implementations. Yeah. So okay.
Okay.
Shall we conclude my talk? Okay, you're welcome.
Yeah, actually,
thanks.
Very interesting talk and very interesting discussion. Thank you all for contributing to this.
Okay, I will stop sharing my screen now.
Okay.